Today we are going to estimate the mass of a black hole from position data of an orbiting star. In this lab, we make the assumption that the only force acting on the star is the gravitational pull on the star by the black hole. To find the mass, we will create a model that finds the velocity, then momentum of the star. We then find the change in momentum over time, which is equal to the net force. We can also use the momentum values we solved for to find the parallel and perpendicular components of the net force. These calculations are approximations since we are doing them in time steps. Because of this, the mass output of the black hole will vary from calculation to calculation. To best approximate the mass, I took the average of all the masses and got it to be 2.11 E34 kilograms. Key concepts of this lab is the momentum being able to be broken into perpendicular, change in direction, and parallel, the change in magnitude components. We are then able to apply this to the force using the momentum principle. F net equals change in momentum over change in time, and can break the force into perpendicular and parallel components. Also, since we made the assumption that the black hole is the only object acting on the star, the net force in our experiment is going to be the gravitational force of the black hole on the star. We can use this force in the gravitational force equation to solve for the mass of the black hole. We also utilize the position update and the velocity version of the momentum principle to obtain values for the momentums and forces. For my code, I started with initializing the star's mass and the time step, which is 86,400 seconds, or 1 day. Then in the upper right, I indexed the star's position data to get the velocities for each time step. Moving to the bottom left section of code, I then pulled those velocities at each time step to get the momentums and change in momentum. Now that I had change in momentum, I could divide by the time step to get the rate of change of momentum, which is equivalent to the net force on the star. The code in the lines following that is finding the parallel and perpendicular components of rate of change of momentum, which are equivalent to the force components and their respective directions. I find these values so that there will be arrows representing the force components on my model. However, the components are not necessary to find the mass of the black hole. All we have left to do is rearrange the gravitational force equation for the mass of the black hole, plugging in our solved F net value. The change in momentum, parallel component of the change, and the perpendicular component of the change are shown by the orange, purple, and blue arrows respectively. The arrows are changing in size and direction throughout the orbit because the magnitude and direction of the force on the star and the motion of the star are changing throughout the orbit. I concluded that the mass of the black hole was approximately 2.11 E34 kilograms. I obtained this through the approach outlined earlier. Splitting the change in momentum is very useful for visualizing how it is changing. In the model, you can visually see how the magnitude and direction of the momentum is changing. For example, as the star moves away from the black hole, the magnitude of the momentum, the parallel component, is increasing while the perpendicular component, the direction, is changing to point towards the black hole. Since we assumed the black hole's gravitational force was the only force affecting the star, we are able to use the gravitational force equation to solve for the mass of the black hole. What does it mean? Net force and its components have the same values as dp/dt and its respective components, but they represent different things. Force is the push or pull on our object of interest. Multiplied by time, this causes the change in momentum of our object. Rate of change in momentum has to do with how the object's motion is changing. This also has time factored into it so that we have a rate for that value. If we're looking at an object as our system, force is going to be an external quantity, while rate of change of momentum is an internal quantity. This means the force is going to be an external object acting on our object of interest, while momentum is going to be a quantity that is intrinsic to our object of interest. What if we replace our black hole with a new one? In this hypothetical scenario, we are keeping all of our position data, orbits, and the black hole location the same. Since all of this is the same, we would not find a new mass for the black hole. The reason for this lies in our code since all the velocities are going to be staying the same, which leads to the momentum and dp/dt values staying the same, which gives us the same net force and therefore the same mass when we solve the gravitational force equation.